What if a beam of light could tell you exactly what was burning before the smoke alarm ever went off? That question led us down a path that started with a sensor, a chimney, a lot of overnight data, and ended with a pretty surprising statistical answer. This is the story of how a human researcher and an AI analyzed 19 hours of sensor data, together formed a hypothesis designed to test, and found a signal hiding in plain sight inside the math. Measuring smoke coming out of a chimney sounds simple. You shine a light across the stack. If smoke blocks the light, you measure less of it on the other side. That's opacity. How much the beam is blocked. But here's the problem. A bug flying through the beam looks like smoke. Condensation looks like smoke. Even temperature changes can fool a basic opacity sensor. The Rainier 5 sensor doesn't just measure how much light gets through, it also measures the wavelength of the light, essentially its color, tracks how the color shifts when something enters the beam. And it does this 10 times per second, storing the last 60 seconds of readings on a rolling memory buffer inside a small microcontroller called an ESP32. After a night of monitoring, we had a data set, 19 hours of clean air followed by 2 deliberate fire tests right at the end. The first fire used inkjet printing paper, the second used popcorn bags with butter residue, 2 completely different materials, 2 very different fire plumes. Here's where the collaboration began. The researcher uploaded the raw sensor file and started asking questions. The AI helped parse the numbers, identify patterns, and build the analysis by not replacing the human's judgment, but by accelerating it. The human noticed something in the live dashboard that the raw numbers alone didn't make obvious. During both fire tests, the kurtosis of the wavelength signal goes up, while the kurtosis of the light intensity went down, at the same time in opposite directions. That's the hypothesis, and to understand why it matters, we need to talk about kurtosis actually is. When a sensor sits in clean air and nothing interesting is happening, it's reading very randomly. A little high, a little low, clustered around a middle value. Plot enough of those readings and you get a bell curve, what mathematics call a Gaussian distribution. The bell curve has 2 key properties. It's symmetric and it has a specific amount of tail, how far out the rare extreme values reach. That tail behavior gets a number. It's called kurtosis. For a perfect Gaussian, kurtosis always equals 3. Kurtosis tells us about the shape of the data's distribution. A low kurtosis means your data is spread out flat. Values are scattered everywhere. A high kurtosis means your data is very sharp peak. Most values are clustered tightly around one number, with occasional extreme outliers pulling the tails out. The formula raises each deviation from the mean to the 4th power before averaging it. That 4th power is key. It makes kurtosis extremely sensitive to rare, extreme values, much more than standard deviation. Here's the equation. X sub I, each sensor reading. Mu is the average. Sigma to the fourth is the standard deviation raised to the fourth power, which normalizes the result so it cancels out. Kurtosis is always dimensionless. You can compute it on lux readings and on wavelength readings and compare them directly, even though they're in completely different units. Here's the key insight. Random sensor noise stays Gaussian no matter how noisy it gets. But when smoke aerosol particles enter the optical path, they don't add random noise. They force the detected wavelength to lock into a specific scattering value determined by the size of the composition. The distribution snaps from a broad random bell curve to a sharp peaked spike. Kurtosis shoots up. Meanwhile, the light intensity blocked and suppressed. This distribution flattens, and its kurtosis drops. Two channels, two opposite responses, one clear signal. To test the hypothesis, two fires were burned deliberately at the end of the overnight monitoring session. Fire 1 was inkjet printed paper. It produced dense, dark smoke. Opacity shot up to nearly 81%. The wavelength shifted 34.5 nanometers from baseline. Kurtosis divergence was immediate and large. Fire 2, the popcorn bag with butter residue. A very different plume. Opacity peaked at 31%, much lower, but the wavelength shift was nearly 30 nanometers. The oily aerosol from the butter scattered lightly, selectively, even without producing dense black smoke. In both cases, the pattern held. Wavelength kurtosis rose sharply, lux kurtosis fell. The divergence between the two channels was the detection signal, and it appeared within the first 60 seconds of each fire, well before a traditional smoke sensor would have triggered. This is not something you can see by watching opacity numbers. It took looking at the shape of the distribution, the fourth moment before, of both channels simultaneously. That's what made the collaboration productive. A human noticing a pattern on a live display and an AI helping to quantify and explain it statistically. The ESP32 keeps a circular buffer of 600 readings for each channel. As each new reading arrives, the oldest one drops off. Kurtosis is computed on this rolling 60-second window continuously. Why 600? It comes down to a statistical trade-off. Kurtosis precision improves with more samples, but only as the square root of sample count. Going from 600 to 1200 points only reduces uncertainty by 29%, while doubling the memory needed and risking dilution of the onset signal with pre-fire baseline data. 600 double precision readings per channel uses about 9.5 kilobytes of RAM. Well within the ESP32's budget, it's enough history to see the fire. Adding more doesn't help nearly as much as it costs. Smoke measurements has traditionally relied on opacity alone. how dark the plume is. That tells you something burned. It doesn't tell you what burned, how dangerous the emissions are, or whether the event is a fire versus a false alarm. What this work suggests is that the spectral distribution of light, not just its intensity, carries a fingerprint of the combustion material. Different aerosols lock the detection wavelength to different values, different kurtosis signatures, potentially different materials. If this pattern holds across the replicate burns of the same material, and what's the key question still to be answered, it opens the door to something genuinely new, a low-cost embedded sensor that doesn't just detect smoke, but characterizes what's producing it in real time on a microcontroller without sending raw data to a cloud server. It has implications for residential chimney monitoring, industrial stack compliance, wildfire early detection, and indoor air quality. Anywhere you need to know just not that something is burning, but what. And none of this analysis happened in isolation. It was a back and forth, a human asking questions that shaped where the AI looked, and an AI surfacing patterns the human could then interpret physically. That's what productive human-AI collaboration looks like in practice, not one replacing the other, but each doing what it does best. To summarize, Gaussian distribution describes normal sensor noise. Kurtosis measures the shape of that distribution, how peaked or flat it is. When aerosol smoke enters an optical beam, the wavelength channel becomes more peaked and the intensity channel becomes flatter. At the same time, and that divergence is the detection signal. A 60-second circular buffer of 600 samples gives the ESP32 exactly enough history to catch that signal onset without wasting memory or diminishing statistical returns. The white paper behind the video goes into the full math, the memory calculations, and the recommendation for the next phase of testing. I'll put a link in the description. If you want to follow the project as more test burns happen and the material library grows, subscribe. There's a lot more signal left to find. I think this is enough high science and kurtosis for anyone, so I'm going to sign off here. You can go get my products at Smokeless Chimney and have a good day. Keep the science going.